All right, let's dive into the hidden math that, believe it or not, is quietly running our entire digital world. We're about to see how it's even possible to solve what feels like a million different problems all at the exact same time.
I know, it sounds like the beginning of a really weird joke, right? But the answer is actually a single, incredibly powerful mathematical idea. And trust me, this is going to connect a whole lot of dots you probably didn't even know were there. So the answer is that they all rely on solving these massive systems of what are called linear equations. Now, don't let the names scare you. Just think of them as simple rules, like 2 apples plus 3 oranges cost $10. Now imagine millions of those little rules all tangled together. Well, that's the invisible architecture holding up so much of our modern world. I mean, just look at the sheer variety here. You've got the physical stress on a bridge truss, then you have the flow of money in an entire economy, and then you have the algorithm that's ranking literally billions of web pages. They seem like they have absolutely nothing to do with each other, but mathematically, they all boil down to the exact same fundamental problem. Here's the real challenge. Each of these problems has countless different moving parts, and they're all connected. The goal is to find that one single sweet spot, that one perfect set of values where every single one of those millions of conditions is perfectly satisfied all at once. So, how on earth do you manage millions of equations without completely losing your mind? Well, you need a hero. And in this story, our hero is the Matrix. It is a tool designed for one specific thing, bringing order to absolute chaos. Okay, this is where the magic really starts to happen. On the left, you've got your equations, looking all messy with their x's and y's. And on the right, that's what we call an augmented matrix. Seriously, just think of it like a spreadsheet for your math problem. We just strip away all the letters and focus only on the numbers. Suddenly, it's clean, it's organized, and it's ready to be solved. And the process itself? It's surprisingly straightforward. It's almost like a recipe. You take your equations, you pop them into this matrix format, you follow a few simple, repeatable steps to clean it up, and then, bam, the answer is just sitting right there, waiting for you. So when I say we simplify the matrix, what does that actually mean? Well, it's not random. We're trying to sculpt this block of numbers into a very specific, perfect shape, a shape where the answer becomes totally and completely obvious. This perfect shape has a fancy name, reduced row echelon form. Yeah, it's mouthful, so everyone just calls it RREF. You can just think of it as the solved version of the matrix. The whole goal is to get this clean pattern of ones and zeros, because that structure perfectly isolates each variable, telling you exactly what it's equal to. Once you get your matrix looking like this, all the hard work is done. Okay, so let's go back to our earlier example. This is our starting point. This is the matrix for our two little equations. This is the puzzle we need to solve. And after we apply those simple steps, boom, this is what we get. Just look at how clean that is. You've got that nice diagonal of ones and zeros everywhere else. This right here is RREF. This is the solution. Because now, watch how easy this is. We just translate it back into equations. That top row, it just says 1x plus 0y equals 3. In other words, x equals 3. The second row says 0x plus 1y equals 2. So y equals 2. That's it. No more work. The answer is literally spelled out for us. So this seems totally foolproof, right? A perfect, logical system. But what happens when we let computers, with their ability to do trillions of calculations per second, handle this? Well, that's when things can get a little weird. And this is where our story takes a really sharp turn. Because in the real world of computers and programming, there are these hidden dangers. A glitch in the matrix, if you will. You'll see quotes like this in computational math textbooks. It's a really stark warning against using a common shortcut. And what it's telling us is that even a method that is 100% correct in theory can be dangerously, catastrophically wrong in practice when a computer is doing the number crunching. So what's the deal? The problem is something called round-off error. You know how computers can't store numbers with infinite precision? At some point, they have to chop off those decimal places. And usually, that's totally fine. But sometimes, those tiny, seemingly insignificant little rounding errors can get magnified over and over again during a calculation, just snowballing until the final answer is completely, wildly incorrect. And look at just how bad this can get. This is a real example from a textbook. The exact correct answer was x equals 1 and y equals -1. Simple enough. But the computer's answer,
It wasn't even in the same ballpark. It got the sign of X totally wrong and was way off on the value. It's just garbage.
This wasn't just a tiny inaccuracy. The size of the mistake was bigger than the size of the actual correct answer. Now imagine you're an engineer and you use that computed result to design a bridge. I mean, it would be absolutely catastrophic. This is the kind of hidden risk that lurks in financial models, in climate simulations, in all sorts of critical systems.
So how do we know if a particular matrix is a ticking time bomb? Well, mathematicians came up with a really clever diagnostic tool. It's called the condition number, and you can just think of it as a fragility score for your problem. If the number is low, close to 1, your matrix is stable, it's trustworthy. But if that number is high, that's a major red flag. So what was the condition number for that simple 2x2 matrix that gave us that horrible answer? Get this, it was almost 2.2 million. That is the math basically screaming at you, danger. This system is incredibly unstable. It was the mathematical equivalent of being balanced on the head of a pin.
Okay, so we have this powerful tool that can also be incredibly delicate. Now, let's scale that idea up, way, way up, to one of the biggest computational problems ever conceived. And this brings us right back to our original question about Google. You can think of the entire World Wide Web with its billions of pages and trillions of links as one single gigantic system of interconnected linear equations. Because at its heart, Google's original PageRank algorithm, the algorithm that literally changed the world, is an enormous linear algebra problem. It assigns an important score to every single web page by treating the entire internet as one massive matrix, and then solving the system. It's the exact same math we've been exploring, just on a scale that is truly mind-boggling. And this really leaves us with a final, crucial question, doesn't it? We've just seen how even simple, elegant math can have these hidden breaking points. It really makes you wonder, what other complex systems that we depend on every single day, in our finances, in engineering, in our digital lives, are resting on foundations that might be just as fragile as they are powerful?